Okay, so first, thanks very much for the invitation to speak here, and thanks very much for organizing this seminar series every time. Some of the stuff that I'll talk about today, I did together with Andrei and Andrei Lucas at Oxford. And I'll be talking about non-ambient flops and what we can learn from them. So flop is what I'm going to be talking about, is an example of a topological transition between Calabi-Yau threefolds, or at least that's the context in which I'll be talking about these. And typically in the kind of algebraic descriptions that we use of Calabi-Yaus, or whatever space we're interested in, we deduce these from flops of the ambient space. So by non-ambient flop, I mean a flop that isn't induced by one in the ambient space. And what I'll talk about is how to discern the presence of these non-ambient flops, how to explicitly perform them to get a description of the space on the other side, and what kind of insights one gains from understanding these. So I'm going to be talking about complete intersection Calabi-Yaus in particular, and they're a particularly simple example, but the below techniques will also generalize to other common or important constructions like toric complete intersections, generalized complete intersection Calabi-Yaus. So together, these three sets of manifolds provide quite a tractable corner of the landscape, and they're also quite a fruitful arena for model building. So good reasons to focus on these kinds of manifolds. And why flops in particular? Well, the physics through a transition like a flop can often be smooth, so flops can connect phases of the theory into a larger moduli space. So you understand a web of theories if you understand, or you understand the web of the moduli space that your theory can move into. And to analyze limits of the physical moduli space, which is often important these days, then it's important to understand the extended Kähler cone, which is this extended Kähler moduli space. Additionally, understanding flops, as we'll see, can allow one to often write down a bunch of the data that you need for model building purposes. So the goals in my talk will be to give this kind of new twist on an old story. CICYs, of course, are quite an old story. And some of the things that we'll get are how to read off these non-ambient flops straight away from the complete intersection data. And I'll use this to characterize the CICY list. So we'll see that almost all CICYs actually emit flops. And moreover, in almost every direction that you move in Kähler moduli space through the Kähler cone boundaries is a flop. Additionally, we'll see that many CICYs actually flop to themselves as well, so isomorphic Calabi-Yaus. Another new tool is how to perform these flops explicitly, so I'll explain exactly how you can do this as a continuous process and what the description is of the space afterwards. And we'll see that there's a kind of a novel situation which you wouldn't see from these ambient space flops, which is that many of these Calabi-Yaus emit infinitely many flops. So the extended Kähler cone we'll see has this kind of fractal structure. Another new tool is that often we'll see, if you understand the flops, you can read off all the line bundle cohomologies from the CC configuration matrix alone. So let me introduce what a flop is. So a flop is a codimension 2 operation, which means, so in codimension 1 you'd have divisors, in codimension 2 you'd have curves. So what you do in this case is you cut out a curve and you replace it with another curve. So a classic example is when you change the triangulation of a toric variety. So if you had four rays of your toric variety, which are the vertices of these squares, then these different ways you could triangulate this square by putting the line in either of these two cases, that corresponds to putting in a different kind of curve. So this is a flop on a toric ambient space. And often these descend to the Calabi-Yau hypersurface or complete intersection that you are dealing with inside this ambient space. But importantly, for complete intersection Calabi-Yaus, the ambient space doesn't admit any of these kind of flops. So they're a good place to look for these non-ambient flops because these are the only kinds of flops that there are. A flop can be achieved continuously. This is one way to think about it, by shrinking the curve to zero volume, which gives a singular point, and then growing a new curve, which is called a small resolution. Like I said, this is a codimension 2 operation, which means it's an isomorphism of the space in codimension 1. So in particular, the space of divisors is preserved. So you can consider the same space of divisors and just move between the old Kähler cone to a new Kähler cone. So this is this classic picture in the bottom right. I think you can see my mouse if I move this around. So here's one Kähler cone of your space, and you move into another Kähler cone when you pass through the flop. But you can keep considering the same space of divisors. Okay, the simplest example of a flop is called the Atiyah flop. And here you begin with a singular threefold, which has this local description. So inside C4, this cuts out a threefold. And this the coordinates of the C4 are Y, Z, U, and V. And this threefold has a singularity at the origin, has a singularity where Y equals Z equals U equals V equals 0, because the derivatives of this will vanish. And you can resolve this singularity into a P1. So here's one way to resolve this singularity into a P1. You can introduce an ambient space factor of a P1, which has homogeneous coordinates x0 and x1. And you introduce these two equations, which are linears in the new P1. And so they pick out points in the P1. This first equation picks out a point in the P1. The second equation picks out a point in the P1. And these are going to be generally inconsistent unless, so these two equations will pick out different points in the P1, except when they're consistent with each other, which only happens when YZ equals UV. So this is isomorphic to the space I had before, except when Y equals Z equals U equals V equals 0, because in this case, both of these equations are trivially satisfied, so you get the entire P1. So this resolved this singular point into a P1, but I haven't talked about the flop yet. The flop happens because I chose a particular pairing of Y with U and Z with V, but I could have chosen a different pairing of Y with V and Z with U to perform, when I chose to write down these two equations, I could have chosen a different pairing. Here's the other pairing. And these two choices are the spaces, they give the spaces that are related by a flop. At the moment, those two spaces just look totally isomorphic because this is just a very local situation. You'd have to patch this together as a small part of a larger manifold to understand how the flops can differ. But this is the local description. So now let me also introduce CICYs so I can talk about this kind of situation arising in CICYs. So what is a CICY? It stands for complete intersection Calabi-Yau. So the ambient space is just a product of projective spaces. The Calabi-Yau is given by the intersection of zero locus of a set of polynomials inside this ambient space. So here's an example. So this matrix on the left means that the ambient space is a P1 times a P4. This is a CP1 and a CP4. And I denoted the coordinates x and y. And then you have two equations. These columns are equations. One equation is linear in the x and order 4 in the y, and the other one's linear in both. So you get these two equations, which describe your Calabi-Yau sitting inside the space. In general, for this kind of matrix to describe a Calabi-Yau, the sum in each row has to be the projective space dimension plus 1. So that's going to be true in all the cases we discuss. The superscripts here denote the orders. And the subscripts are just labeling the different kind of functions. So this is an example of a CC, and we're going to actually come back to this one a bunch of times. This is called favorable. This kind of description is called favorable if the dimension of the space of divisors is just the same as that on the ambient space. So you can just restrict divisors on the ambient space to completely cover your space of divisors on your Calabi-Yau. And it's called Kähler favorable if the Kähler cone is just exactly the Kähler cone of the ambient space. Which also implies that it's favorable. And for simplicity, I'll only discuss these kind of cases. So that means that the Kähler cone will always just be sort of the positive quadrant in the natural in the natural basis of divisors. So now I can talk about non-ambient flops, now that we covered the Atiyah flop and CICYs. So here's this example from the previous slide. I chose to rewrite the equation in a little bit of a different way, where it's a matrix equation. This just gives back the two equations I had before. But it's easier to see here that you only have a single solution in P1. So this gives two linear equations in P1, and again, they pick out 2 points in the P1, just like in the Atiyah flop case. And consistency of this demands that the determinant of this matrix is 0, which gives this kind of equation, F1G2 equals F2G1. So this has to be true inside the P4 in order for us to actually be sitting on the Calabi-Yau. And you also get an entire P1. Analogously to the Atiyah flop, you get an entire P1 when all 4 of these polynomials are 0. because then the rank of this matrix reduces even further. So you just pick out the entire P1. So this space looks like a set of, at certain points in this Calabi-Yau, you have this entire P1, which has been resolved. So you can shrink these P1s back down if you like. And the singular manifold is just given by this determinant equation, setting this determinant matrix to 0. This misses out these extra P1s. So they're gone. And this is exactly analogous to the Atiyah flop singularity. You can also see that this is actually just a tuned quintic. So it's a specific polynomial choice of a quintic equation inside P4. So quintic, I mean order 5 sitting inside P4. And this is just the known, very well-known story that you can reach some Calabi-Yaus from a conifold transition from another. So in this case, you start with a quintic Calabi-Yau, you tune it until it takes this special form, and then you can resolve these P1s. So that's the process of the conifold transition. It also means you can easily count the shrinking curves because you can just compare the Euler characteristic of this quintic space to the space afterwards. You could also count it more easily in this way I said here. So, okay, so this is the singular space that we get upon boiling down the P1s, and I want to talk about the other way in which you could resolve the P1s to get the flopped space. So there's the example again. So analogous to the Atiyah flop, what we're going to do is choose the other pairing of the two linear equations. So before I had F1 and F2 sitting in this first equation, and now I've exchanged F2 and G1. So this is totally analogous to taking the different pairing of the 4 coordinates in C4 in the Atiyah flop example. But of course this looks different because these aren't just coordinates inside a C4, so the degrees of the monomials don't match up. This first term here has 3 more powers of y than this guy, and similarly in the second one. So this doesn't look like maybe a sensible thing to do, but it's quite easy to see that actually you should just understand that this flopped space is a complete intersection inside a toric variety. So in particular, this is the weight system that you need to have in order for these equations to be consistent. So this 3, which I highlighted in yellow. So these 2 rows of the weight system, they correspond to 2 scalings that you're allowed to perform, projective scalings. And this would have been a 0 in the case when I had a P1 times P3, but I'm introducing this 3, which corresponds to fibering this P1 over the P3. And this 3 precisely makes up the difference in the second monomial as compared to the first. So this makes these equations consistent. And then these 2 equations have these weightings under these scalings. Okay, so that was a special case. There's a more general situation where you have a Pn in the ambient space and a whole bunch of linear equations. So you can see by generalizing what I just did that if you have such an example, so here's one, where you have 3 linears inside a P2, which you can also write in this sort of determinantal form, matrix form. So this is the 3 linears, the top row contracts with this to give one of the linears and so on. That describes your Calabi-Yau inside this space. And then the analogous thing to do to what I did before is to take the transpose of this matrix of polynomials. So if the original Calabi-Yau was given by this matrix equation here, then the second Calabi-Yau, the one on the other side of the flop, is given by taking the transpose of this matrix and then reinterpreting the ambient space as toric with some appropriate weight system. So this gives the description of the flopped space as a complete intersection toric variety inside a toric variety. And just as a slight aside, the new Calabi-Yau is isomorphic to the original if these vectors underneath the ones are equal. And we'll come back to that in a minute because we'll be able to exploit this fact. So if these columns underneath the ones are equal, then you see that the transposing this matrix actually does nothing. So you can immediately see that this Calabi-Yau admits a flop to itself. This was just one example of the kind of rows that can give these non-ambient space flops. But here are some other examples. If you have just a 2 and then a bunch of zeros, or if you have a 2 and a bunch of 1s. So this means just a quadratic equation inside the P1. And here are a bunch of linears and a single quadratic inside some Pn. These you can also understand with sort of similar methods and see that they give flops as well. So here are some applications of this kind of understanding these kind of flops. So there are 4,874 Kähler favorable CICYs and about 30,000 boundaries for the Kähler cones in those spaces, through which there could be a flop or could not be a flop. And you can just check for the presence of these kinds of flops that I described by looking at whether the rows have these forms that I just discussed. This is slightly not true because the true number is a little bit smaller because there are some what are called ineffective splittings where actually it's not truly a flop because nothing shrank, but this is a really small number. And you can check this by comparing to the Euler characteristics of the singular space to see if something actually shrank or it didn't. So what you see if you just carry this out, I mean, it's very easy. If you just carry this out is you find that pretty much every single CC admits a flop, first of all, admits one of these non-ambient space flops. You also find that essentially all of the directions out of the Kähler cone are flops, more than 29,000 out of about 30,000. So the conclusion is that these non-ambient flops are not only possible, but they seem to be very much generic in this space, in the set of CCs. Second application is that you see these situations where you get infinitely many Kähler cones. So how do we see this? So infinite many flops, infinitely many possible Kähler cones, same thing. So here's an example. This guy's called 7761 in the CC list. This is a dimension 2 example. And we have 5 linear equations or bilinear equations in these 2p4s. So the fact that this row has all 1s tells you that you can perform one of these non-ambient flops. The fact that underneath each one, the vectors look the same, they're not vectors, but it looks exactly the same under each of these, that tells you that the flop will produce a Calabi-Yau, which is isomorphic to the original. And you see you can do this in either direction because of this symmetry. So both Kähler cone boundaries are flops to isomorphic Calabi-Yaus. But this means that once you pass through the flop, so let's look down this picture. If I pass through this boundary here into this flopped region, then this line here becomes analogous to this line here. And I know that I can flop through that line as well. So now I can flop through here as well. And similarly, I can do this on the other side. And the conclusion is that you have infinitely many flops, which pass through infinitely many Kähler chambers. So this you can immediately see from, so the punchline is you can immediately see from this configuration matrix that you have these infinitely many flops, and that the structure of the Kähler cone is precisely like this. This is a kind of a novel situation because this wouldn't happen if you were only considering flops from a toric ambient space. Because flops on a toric ambient space, they arise from changing the triangulation of your polytope that defines your ambient space. And the number of triangulations is always finite. So you shouldn't be able to perform infinitely many flops of your ambient space, so you shouldn't be able to see these kind of situations where you get infinitely many flops of your Calabi-Yau. So that was a kind of a simple example of when this happens, but just to draw some pictures of high dimensional cases where this happens. So here's a 5-dimensional Picard lattice, 5-dimensional space of divisors. This one is 4 dimensions. So the Kähler cone is 5-dimensional, 4-dimensional respectively. This guy on the right is kind of well known, it's tetraquadric. So again, by exactly the same methods, maybe I didn't mention this. If you have a single 2 in your row, this also tells you that the CC is isomorphic on the other side. I didn't deal with this case explicitly, I only dealt with these cases explicitly, but you can do similar things here and see that a flop in this direction will produce an isomorphic Calabi-Yau, and so it does it in every single direction. Similarly here, in every single direction. So the picture that you get of the Kähler cones, I mean, here I'm pretending that the Kähler cone is 3-dimensional. I'm taking a slice through it. I'm sort of looking down from above. And you get this kind of fractal structure. So this central triangle is a slice through or a projection from the top of the original Kähler cone. And then when you pass into the next Kähler cone, say this one, then you know that because this space is isomorphic, you can continue to do flops out of the other 2 boundaries because those boundaries have just become analogous to these. So you can pass in here, you can perform this flop or this flop, and then when you get here, you can continue to do the same. And you can do this infinitely many times. So you end up with this, this structure of infinitely many Kähler cones, or sort of a fractal structure. Okay, a third application of non-ambient flops is that in many cases, this allows you to just immediately write down all the zeroth cohomologies. So a simple example is when you have a flop between two isomorphic Calabi-Yaus. So how do you determine the new Kähler cone when you pass through the situation, when you pass through to the new Calabi-Yau? It's well known how objects like the triple intersection numbers or the second Chern class of your space change under a flop. They're changing because you're removing a curve and putting in a new one. So things like intersection numbers certainly change, but it's well known precisely how they change. And the fact that you know the space afterwards is just the same as the original Calabi-Yau means that the change of these objects must be undone by a basis change. Meaning you rotate your basis from the Kähler cone of the original space to the Kähler cone of the space afterwards, and these objects should go back to themselves. And then the new cohomologies, we already knew how to get the cohomologies inside this Kähler cone, this new Kähler cone, because we know the new second Chern class and new triple intersection numbers, and these totally determine the index. And inside the Kähler cone, you have a vanishing theorem, so the zeroth cohomologies that are just given by the index. So all you really needed extra was determining the new Kähler cone. So here's an example. This is a case because we're the two here. Because we have a single two here, we know that flopping through this direction is going to give an isomorphic Calabi-Yau. So you know that if you pass through this line here, you're going to pass into the Kähler cone of an isomorphic Calabi-Yau. And then if you just compute C2 and D, how they change under the flop, and then you find the basis transformation that puts them back to themselves, you find that this is the edge of the new Kähler cone, which has this sort of gradient of -1/4. So this maps out the entire effective cone for you. It tells you exactly how the Kähler cones fit together. And then because you already know C2 and the triple intersection numbers, you can just write down all these cohomologies straight away. Okay, the fourth application is to extend this to toric, complete intersections, and generalized CICYs, which I haven't discussed, but I'll explain in just a second. So the extension to the toric case is actually super straightforward. I mean, the above were really special cases of toric cases where one side of the flop was consistent with having a product of projective spaces as the ambient space. But here's an example where that wouldn't be consistent. You might have an order 2 polynomial here and order 3 here, and order 5 and order 4 here and order 5 here. So this is not consistent with having a product of projective spaces as your ambient space. In particular, x0 has to have one, has to scale like a y as well as an x in order to make this consistent. And then following the same prescription for the flop, you would just switch F2 and G1. And now you see this is consistent with a different kind of ambient space where x0 has scales like 2 y's, like y squared, as well as like an x. So yeah, it works exactly the same here. For generalized CICYs, so I won't explain too much what these are, but they're like CICYs, except you're allowed to put a negative entry in this matrix that defined it, which defined the equations, which means that your Calabi-Yau is defined as the intersection of not a set of polynomials, but polynomials where you're allowed to have negative powers of your coordinates, which normally wouldn't pick out just a zero locus. You'd also have some sort of pole locus. But for special choices, you can pick out a Calabi-Yau. So these are a relatively recent development. So for example, here's a generalized CICY on the right, which was used just last month in some model building work. So it's this fifth row here that's the sort of generalized direction. This -1 would not be allowed if you just had a CICY. These other directions are totally fine. And what you can at least see is that the flops that I've talked about so far, they can certainly be performed in all of these first 4 directions for the same reasons that you can do them for CICYs. So you can perform a flop in this direction because it's just 1s. You can perform a flop in this direction because it's just a 2. So this generalized CICY at least admits, this also happens to be Kähler favorable. And so there's 5 boundaries to the Kähler cone, and through 4 of them, you can flop to a space which you can easily write down. And the flopped space is just some generalized. So it's a toric complete intersection, but it's generalized in the same way that these CICYs are generalized. You'll also have these negative powers in some of your norms. You might also be able to flop in this 5th direction, but this is actually not as clear to me. It sort of looks like this is a flop, but I don't totally understand this one. At least in these 4 directions, you can certainly perform flops on these generalized CICYs. So what are some of the extensions of what I've talked about so far? So this is the content of the talk is finished. So here's one extension you could do. You could try to classify all of these non-ambient flops for all CCs, toric. There'll be intersections, generalized CCs to better understanding of the web of Calabi-Yau threefolds. So what I talked about so far was some particular examples where you can perform these non-ambient flops, but it's not clear that these are the only ones. And one should perform a more systematic study of these, and especially in the case of generalized CCs where it's a little bit less clear what's happening. This clearly allows you to try to characterize the different structures for the extended Kähler moduli space. So these fractal cases that I discussed, cases we have finite chambers, what are the different things that can happen, and so on. There's also clearly a connection to to gauge linear sigma models, because these sigma models, moving into these different Kähler cones describes different phases of the sigma model. So there's clearly some connections here, and maybe you could learn something in one direction or the other direction. I only discussed the zeroth cohomologies because that's the most obvious, that has the most obvious connection to these flops and to the space of the effective cone and Kähler cones. But it would be nice to understand the relation of the flops of the higher cohomologies, relation of the flops to the higher cohomologies, and see if you could read those off as well in some kind of similar way that you can do this with the zeroth cohomologies. Okay, that brings me to the end of the talk. So thanks for listening, and please ask some questions if you want.
Great. Thanks a lot, Callum, for your very nice talk. We already have a question. We have quite a few questions now. Federico, you're first. Oh, sorry. Before we go on to questions, let us thank Callum for his talk using our emojis. And now, once that's done, Federico.
Hello, very nice talk. So I have a question. So if we take the conifold, the non-compact conifold, and we go in the resolved phase, we know there are two different ways to do it connected by a flop. And we know also that all CICYs are connected by conifolds, in which I have now multiple conifold points, and I can go to the resolved phase. So naively, I would have expected that all CICYs have this non-ambient flops. My question is, can you show and prove that some CICYs don't admit such flops, or?
You can certainly show that some don't admit them, yeah.
Okay, I see. So something goes wrong with this naive argument. Because I'm saying if I have just the non-compact conifold, I can resolve it in two different ways connected by a flop. If now I look at conifold points in a compact Calabi-Yaus, I will have many of them, like the example you gave as 16 conifold points and goes to the quintic. And so you say that sometimes there is an abstraction in performing the flop, like extending this this basic conifold flop to the.
I guess maybe the point is, I mean, for example, you can just have a Kähler cone, which you can just have your effective cone be just a Kähler cone. No other flops available. That happens, for example, for the bicubic. So in that case, there are no flops available. And I guess you're saying the fact, but you're saying Calabi-Yaus are connected to each other by conifolds. So how can this be?
Yeah,
but I guess the point is the conifold goes in one direction. You would start in such a space, and then you would go from a conifold to a different space. I guess you couldn't get to this space by doing some resolution. This wouldn't be the resolution branch of the other Calabi-Yau. This would be the other branch, the deformation branch. Does that make sense?
Okay, so it's like a conifold transition, only traversable in one direction, you're saying?
That's what comes to mind. I'd have to have a think, but that sounds...
If it's like this, it's very interesting. I didn't know it was possible. I always thought you can go right and left in a conifold transition. But okay, thank you very much. It's a super interesting talk. Thanks.
Okay, thanks.
Next questions from Ivan.
Hi. So I just wonder, like, if you have a compact Calabi-Yau or non-compact Calabi-Yau threefold, so we have a divisor, like some rational surface, for example, a del peso, then if I want to do a flop of the Calabi-Yau threefold by blowing down this divisor, this del Pezzo, for like a lower del Pezzo, and eventually the Hertz group or a P2.
Sorry, could you say that you had a threefold and you want to blow down a del Pezzo? Is that what you said?
Yeah, I want to blow down a surface in it, so that is still a flop of the whole Calabi-Yau threefold.
So I mean, in a flop, you shrink a curve, right? Not a.
Yeah, I shrink a curve in the divisor.
Okay, yeah.
You
shrink a curve
flop to another divisor, so I mean, it's still a bidirectional equivalent of Calabi-Yau threefold.
Okay, yeah.
So then I just wonder whether you have a general algebraic description of this kind of flop in your language, because many of these flops could be non-ambient flops. Yeah.
Sorry, a general what description?
General like algebraic description of these algebraic equations.
So for any given, I guess the question is, for any given Calabi-Yau, can you understand every flop?
Yes, so you'll start with some kind of like toric hypersurface or toric CICYs, these kind of constructions.
Right. So I don't know if every single flop can be understood in the way that I talked about. These are additional flops beyond those in the ambient space, but I don't know if every single flop can be understood with this kind of method. I mean, first of all, yeah, I had to describe my space as a toric, something or other toric complete intersection, but whether every single flop can be seen this way, I'm not sure. I'd have to think about the specific case you're talking about.
Okay, yeah, that's fine. Yeah.
Okay.
Thanks.
So we'll have 3 more questions. Fabian?
Hey, Callum.
Yeah.
It's a very nice talk. So I have 2 somewhat related questions. First of all, if you have this fractal structure for your Kähler cone, for the extended Kähler cone, is there a canonical or a standard compactification for this extended moduli space?
Oh, I have no idea, I think. So I mean, the simplest situation was this one where you had just a 2-dimensional Picard lattice. Yeah, I don't think I know the answer to your question.
And I can sort of reach all these at finite distance.
Reach all of what?
Go through all the flops at finite distance in moduli space. In the extended.
Very good question. You can reach any particular Kähler cone in a finite distance, I would say. But to pass through infinitely many flops, to pass through infinitely many Kähler cones is an infinite distance, I would think.
Yeah, I don't know if I can try to answer the effective theory question. Is that allowed? Or?
Sure.
Allowed by me, if you like.
I mean, any one of these Kähler cones would have a regular, say 4D description if it was, for example, 2A on that threefold, and you can describe flop descriptions in this 4D context, and so the 4D description you can think of as a sequence of these 4D theories, which are connected by these flops as described in the 4D theory, which effectively requires including the hypermultiplets that become massless at the flop locus into the effective theory. And even if there is a change in intersection numbers, that will be something that will come out of the 4D theory, essentially by some loop contribution that will change the intersection number of the 4D theory to the one for the flopped phase. So I would say there is an effective 4D description.
Fabian, was that your question? And maybe I didn't understand your question.
Yeah, maybe. I mean, I don't want to take up all the time, so maybe we take this offline.
Okay, yeah, no problem.
Okay, Antonella?
Hi, can you hear me?
Yeah.
I'm never sure. Thank you for this very nice talk. I have a question about the examples that you gave. In the example that you gave, at least the pictures, all the Kähler cones were nicely, they were nice, right? But if you looked at the case where, for example, or the Schoen case, and you can, I believe, write as a complete intersections in as a Calabi-Yau complete intersection where the Kähler cone has infinitely many edges.
Right. I haven't looked at this one myself.
Yeah, but I think I believe that your methods could be used also to reprove a theorem that Dave Morrison and I proved a long time ago about structure of this Kähler cone. So, and which is still an open conjecture in many other cases. So it could be then your techniques can be extended actually to prove a conjecture in this very large classes of varieties, if it works with the first case.
I see. Okay. Yeah. Well, that sounds very interesting. I'd have to
That's
think
it.
some...
Well, thank you again for the nice talk.
Yeah. Yeah. No, thanks for the question or comment.
Okay. For a final question, Jakob.
Hello. Thanks for the nice talk. I thought in particular this phenomenon of the non-ambient flop was very interesting, and it made me think of something similar. We recently had a paper, so that was a paper by myself and Atiyah and Alexander Westphal. We looked at orientifolds of CICYs, and as a sort of byproduct, we found many cases where we found ways to find conifold transitions systematically, and there also happened quite frequently that you could show that there is a resolution branch. But the resolution branch was not visible from the ambient variety. So it might be cool to also systematically find these resolution branches with no way that's very analogous. Have you thought about such things?
I haven't thought about it, but it sounds very interesting. Yeah, I mean, yeah, exactly. These are the kind of things that are hidden at the level of the ambient space. So anytime that you're restricted in that way to only describe things from the ambient space, you're going to miss these. So yeah, it'll be interesting to apply this to that kind of problem for sure. Thanks.
Thanks.